Okay, hi, and welcome to lecture 21 of Quantum Physics for Non-Physicists. So, first of all, I'm sorry that I've been very late with uploading the lecture this week. It's been a difficult week. What I'll do is today I'll give the normal lecture like 45 minutes, and then I will record the other lecture of this week, which normally would be the Tuesday one, but it will be the Friday one. Okay. So overall, you'll get the 3 hours of lectures in the week. It will just come in a funny order. Okay, so we are going to continue our stroll into quantum thermodynamics. And remember that the last thing we did last time was to try to find a definition of what a thermal bath is in the quantum case, what can be a thermal state. But because we don't know very well, especially for people who are not physicists, what we mean by a thermal bath, a heat bath, then we're going to take a long way around. So we're going to talk a little bit about how we do it in traditional thermodynamics. What's one way of defining, for example, what a temperature is or what a heat engine is, and what a thermal bath is. Okay, so we'll go through all this, and then we'll end up in the quantum thermal state. And I know that in the tutorial, you already looked at some properties of this thermal state that we'll talk about. Okay. So our daily analogy today is between recommendation systems and heat baths. So what I mean by this is that, well, let's go out on a limb and say that human beings are very complex systems. I mean, if you wanted, you could have a microscopic description of like all the neurons in their brains and all the chemicals in their bodies, cells, etc., down to the atom level, right? But when you're trying to use human beings for something, for example, to make money for some streaming service, then you really only need to use some properties of this being, and you just need a very, very simplified model of what this each user is, right? So for example, if you want to do a recommendation of movies that they would like to see, you just need to know a little bit about which movies they watched and liked, and then you match this to this typical user profile that you've built through your machine learning algorithms, right? And through this, you can, for example, recommend new movies that they are likely to like. And every once in a while, you'll find a user that doesn't fit into this typical stereotype. For example, given their background, you suggest a comedy, but this person never watches the comedy and never likes the comedy, right? But these are not the typical users. And if you're thinking about big numbers, like if you have millions and millions of users, you can kind of forget about this atypical cases. Okay. So it's the same thing for a heat bath. So a heat bath in the end is going to be a very complex system, like a gas that's made of many particles, which may interact or not with each other, which may move in different directions at different speeds. If you wanted a total microscopic description of the system, it would be a very complex one. However, if you just want to know how it acts, like how quickly it cools down your coffee cup and to what temperature, you only need a very, very few properties about this kind of system. And it turns out that there's many systems which are typical in a way that you only really need to know a few little properties about them, like temperature, pressure, etc. And we're going to see how to do the same for the quantum case. Okay, so if this idea of like modeling a very complex system through only some variables sounds a bit strange to you, you can think of this analogy as something that's a bit more familiar. And again, just like in this case, sometimes you'll have a system that looks thermal, but will suddenly do something very, very strange, right? It could be that, you know, every once in a while the planets align, all these particles that are moving in different directions, something happens and they suddenly, I don't know, just happen once in a million years to all go up, and the gas behaves in a very different way that you had not planned in your very simple model. But most of the time, for most practical purposes, this model will be perfectly fine. Okay, right? In the same way that here you can have the strange users that don't fit into your typical situation, but if your model is good, then most users will be covered. Okay. You can see how naive I am about recommendation systems based on this analogy. Okay, so let's just try to get a hold of the big picture again and see what we're trying to do. So we talked about this erasure procedure, which is something that connects kind of information theory and thermodynamics. So it connects in particular like information about one bit. So is the bit on the left, the bit can correspond to a gas being on the left or the right of a box. And we saw that if the gas is kind of spread out everywhere, so we don't know where to find any of these particles, if it to be on the left or on the right, then what we can do is kind of attach it to some pulley system. And if this gas is kept at some external temperature T, and we try to pull this, then you get some, if you put some energy into this, so what we call work, which corresponds to this amount, depends on the temperature of the gas, and some constant and another constant. Then at the end of the day, you can have like all the gas on the left, right? So we just push, we put work, and we trade work for this information about where the gas is. Of course, the process is reversible. We could also now just kind of breathe and let this gas expand, okay? Because these are like particles moving in all directions, in particular hitting this wall. We just let it go, stop holding it, let it go. And this will bring our weight up. So we gain work in the process, we gain this potential energy of the work, but we lose information about the gas. Right now it will be spread out over the whole box. And we want to do the same in the quantum case. And you already know how to model some of these things. So for example, for the bit, we'll have a qubit, and we say, well, this case of where we don't know, the bit corresponds to the fully mixed case here. So 0 + 1, 2. And our goal is going to be have it completely on the left, so completely in the 0 state, right? And well, instead of this weight to measure work, we want to have a battery that's going to be a system with this Hamiltonian that looks like a little ladder going up, or in the continuous limit could be just a line. And we say, well, we'll start with some energy E, and we know that we can expect it to go down by some amount. I mean, it would be nice if it was the same amount as in the classical case, but we don't want to assume, right? And we want to do this via some unitary, but we know that having these two systems would not be enough, because if we wanted to do this, we wouldn't have conservation of energy. So this energy needs to come from somewhere, and we say, well, then we want to model some system as a heat bath, okay, which we don't know yet how to model. And we want kind of energy to go from this battery and be deposited in the heat bath, okay? Just like here, this energy that you put in by lowering this weight, in the end is going to be dissipated to this environment as heat. Okay, and we want to find this unitary that conserves energy in the global picture. And our problem now is that we don't know how to model a heat bath, okay? And your problem in particular is that you don't even know what a heat bath is, so we're going to explore this a little bit, see what properties we're looking for, and then we'll find a quantum state that has these properties. Yeah. So just to give you an outline of what we're going to do today. So first we're going to recap, and we already talked a little bit about this in the last lecture, about what are the desired properties for a big classical heat bath in normal thermodynamics. And then we're going to see like how from these properties we can find a way to define temperature, even if we don't know anything about the microscopic properties of the system that we call a bath. Yep. And for this, we're going to have some notion of reversible heat engines, which I'll introduce. Then after this, I'm going to give you a definition of the quantum thermal state, which you've already seen in the tutorial. It's going to be that. We'll get into this later, don't worry about it now. And then we'll start seeing some properties of the thermal state, which should match the ones in traditional thermodynamics, right? And then in the next lecture, then we're going to finally apply this thermal state. We're going to build a heat engine, a quantum heat engine, and we're going to see that it behaves like the best classical heat engines. And then we can finally start looking at this erasure. So now we have finally a model for this heat bath, and then we can look at an explicit protocol for making this process. Okay? And overall, then with this whole thing, then we have thermodynamics of quantum systems like heat engines and fridges, and we also have this connection between information and thermodynamics, computation in thermodynamics. Yeah. So that's the map. So let's just recap. So what's a heat bath in traditional thermodynamics? And this classical image is really this idea of like a gas of many particles. It's very large, and it will eventually thermalize my system of interest, my cup of coffee, for example. So always think that when you talk about a heat bath, is like the recommendation system. It's a very coarse-grained, macroscopic description of a very complex system, but which, for practical purposes, all these complex systems behave more or less the same. Right? It doesn't matter exactly if this one particle is going right or left. In the whole, they behave like as a typical thing. So what properties should it have to be a heat bath? So let's just think about our intuition about it. So it should be a very typical system, right? We should have this idea that most systems, given enough time, will thermalize. Even if I start with a very ordered, well-defined system, I live, I don't know. So for example, I can live, an example would be, it's not a direct example, but I don't know. You're making spaghetti. You start with the spaghetti very ordered, right? Like all the sticks pointing in the same direction. Leave it enough time in the bath, and first of all, it will get the temperature of the bath, and second, it will be a mess, right? If you look at it at any small enough subsystem, it's kind of it's very messy. More concretely, I don't know. Take a cube of ice. Okay. Cubes of ice are like crystals, which means that they have very, very nice kind of structure. They're hexagons. If you look microscopically, it's super, super nice, super ordered, like a very nice lattice. But leave it inside a glass of water or your favorite drink, give it long enough, and it will become very messy. It will kind of thermalize. It will melt. Right? So it should be something that is very typical. Otherwise, it's not. It's just not what we're looking for. In general, we want for something that is much larger than the system of interest. So in your case, like the bath would be your drink, and the ice cube is the system of interest. And we wanted that for practical purposes, it can be described by just a few properties, right? Like this T, P, temperature, volume, pressure, fluidity. And we'll see this later. Because they are so common, they're going to be one required property is that they're going to be useless on their own. This means you cannot extract anything if you just have access to one heat bath. Right, so I don't know, like you have the temperature of your house, but if that's the only temperature you have access to, you can't do anything from this. You cannot create a machine that extracts work from this. We'll see this later. You always need a difference of temperature. We'll see how to prove this. Okay. So we still don't know what temperature is, and there's a very, very nice operational definition of temperature that has very little to do with thermometers or with the microscopic properties of some liquid or some gas. It's fully operational, which is very nice. Operational means that we design some device to do something, we measure how well it does this thing, and then from this kind of input-output behavior of my device, then I can speculate or I can deduce some things about the properties of the systems it interacts with. So let's take the idea of a heat engine. So what is a heat engine? Is something that takes two baths at different temperatures. We don't know what temperature is yet, but don't worry about it. And exploits this difference in temperature to extract some work. Okay, one example would be a train. What we have in a steam train, so inside you're burning some coal, so creating some gas, so you have some temperature hot. You also have access to the temperature of just the air outside the train that is colder than this. And from these two differences of temperature, you build this steam engine that allows you to move the train, and that's what we call work. Yep. So let's just take this example and get rid of all the unnecessary details and what we end up with. So end up with something, a machine, here's a machine, could be anything for now. And it has access to two systems, which we will describe as heat paths, so we don't know yet what they are, but we say that the only property we care about is something called the temperature. Okay, is the label we give to these two systems. It can be very complex or not, we don't know. And what it does, well, it takes some kind of energy from the hot one, and then it breaks it into two. One is going to be energy that it sends to the cold one, and the rest is going to come out as work, something useful. Right? In this example, it takes energy from the hot coals. It releases some to the environment. There it goes in the smoke, and some is stays as work. Okay? And as notation, all this energy that goes just to or from this paths we call heat. Okay, so these are forms of energy. Work and heat are forms of energy, and we represent it by Q. So heat is energy that is just coming directly from the bath. We don't know exactly in what form yet. We don't have a model for this, so we don't know how this energy is coming. Could be anything for now. Work, on the other hand, is this very ordered energy, like this weight that we lifted and know then exactly how to use it. Or energy that's transformed by, for example, this could be like a solar cell that produces electricity. So this would be then, work in this for work is like energy that we know how to use, essentially. Call it ordered. It's not a very precise definition, but it's just think of it as a working definition. If it's energy that we know how to use, it's what comes out of the engine, we call it work. Okay. So first, let's look at just what we can say from this thing here. And then we're going to build systems with several of these engines, and we're going to derive some properties about this path. Okay. And this is a nice way of seeing how physicists model physical systems. So first of all, we know, like, we can put all of this inside a box, and inside this box, there's no energy coming in or out. And we say, well, let's say we have conservation of energy inside the box. Okay, so by having conservation of energy, what's all the energy going in and out of the machine? Well, inside the machine, you have this heat coming from the hot bath, and this should be the same as what's coming out of the machine, which is work plus the heat going to the cold bath. Okay, so we can just write work is just the difference between the two. And then we can just define the efficiency of this machine. It's like, if it was a perfect machine in the perfect ideal case, which we don't know if it's possible yet, it's not going to be possible. But ideally, we'd want to like take all this heat, all this energy, and convert it all into like electricity, into energy we can use, right? Everything that we need to dump into this environment is kind of excess that we don't want, this kind of garbage. So the efficiency is going to be W over Q hot, right? So if the efficiency was 1, it meant that all the energy that we took from the bath was converted into work, and in general cannot be larger than 1. Okay. And now, of course, that there can be machines that are very, very wasteful, right? It's not hard to build an engine that is a bad engine, right? we just, for example, from a good engine, we can always take a bit of this work and just dump it, just dump a bit of this energy in the cold path, right? And making a strictly worse engine. But now let's think about the best possible engines. So these are the engines that are reversible, which means that you can run them one way or the other way. So you can have from the hot to the cold. So you could have two of them in a circle, for example. Let's say we put work in. We run it in reverse. And then we have one that has work out, that is running the usual way. No. Now, if you have a machine that can run in reverse and is really reversible, reversible means that, well, what I take from the bath above is what I put it, and the same below. Okay. So if I just run this whole system, overall, there's no changes in this bath, right? Because this bath, we say, depends only on the temperature, and I take something out, but then I give it back again, and the same to the cold bath. Okay. So if the engine is reversible, then again, by conservation of energy, the work that goes in this case is going to be the same as the work that goes out in this case, right? The efficiency of running one way is the same as the efficiency of going the other way. And right now, we don't even worry about what this, about the inner behaviors of this machine. And one nice property of reversible engines is that they must all have the same efficiency. And this is very strange. So suppose we have two engines, and that we have the efficiency of engine A is larger than the efficiency of engine B. Okay. So then we run them in next to each other. So here's the hot bath. Here's the cold bath, and we're going to run the engine B in reverse and engine. So this is B and this is A. This one goes like this and this one goes like this. So this energy is the same. When these two energies are the same, then we have here work B and work A coming out. Okay. So what's the difference in work? Work A minus work B. Well, this is going to be the efficiency of A. Whereas definition of efficiency is like this. So the efficiency of A times QH minus the efficiency of B QH, right? So you have QH, efficiency of A minus the efficiency of B. But so if this is not zero, if this thing here is not zero, then this is not zero, okay? Which means that we have a system where nothing is changing on the hot bath because what you take out is what you put in. Nothing is changing on the cold bath. What you put out is what you put in. But somehow you're putting in some energy and you're getting out more energy than you started with. Okay? So this one doesn't change. Of course, microscopically it changes. The particles are not all moving in the same direction as initially, but the macroscopic properties don't change, right? This one also doesn't change. So you have these two very stable systems, and from here you're kind of just extracting this delta W work. And that's essentially what this is, would be a perpetual motion engine. Yes, best possible engines, I mean, in terms of efficiency, yes. Yes. So this would be the example, right? If I have a machine, if I have one that is better than the other, but they're both reversibles, then I can take the worst one, run it in reverse, and then just get work out of the better one. Okay, but then I end up with some extracting work without changing the rest of the system, which is a perpetual motion engine. And that we say, okay, this is just unphysical. That there must be something else going on here, which means in this case we cannot represent these things as heat paths, etc. So the conclusion is that kind of all reversible heat engines are equivalent. And by a similar argument, you can see the maximum efficiency of any heat engine is the one for the reversible ones. Okay. And this is I mean, for a computer science result that is similar, is like this idea that all computers are equivalent up to polynomial overheads, like this Church-Turing thesis, where some computers will be faster than others, but if you only care about the overall complexity and what problems they can solve or not solve, then they're all equivalent. Okay, so here you can have heat engines that have maybe one works faster than the other, but in terms of efficiency, all reversible heat engines are equivalent. They have the same efficiency, which depends on what? Well, depends on the temp. It can only depend on the temperature of the two baths, of the hot and cold bath that it's connected to. So we're going to find it. We're going to try to find what this efficiency is, and in the process, we're going to define what this temperature is. And for that, we need a system that's a bit more complex than this. But so let's build it. So let me start with a hot bath, and here's the cold bath. It's also very large, but I need the space on the right. Oh. Okay, and I have this engine, let's call it engine A, running here. Cold, hot. Yep. And then I say, well, if all reversible engines are equivalent, and this is a reversible engine, then I might as well say, well, this is equivalent to having a different situation where I can introduce another bath. Okay, it's going to be my reference bath. And then I could think, well, then I can have another reversible engine here and another reversible engine here. And I just have this one running the usual way. And now this one running in reverse. Okay. In this situation, whether I extract work from the hot bath or the cold via this, or if I go via this reference system, reference bath, it should be, in the end, is going to be the same. We'll show this. But that's the idea. So let's say we take from here work A out. From this one, we take work C. And this one, we'd put in work B because it's running in reverse. And the idea, again, is that this whole system here is going to be equivalent to that. And let's take for now that in this example, we take the hotter to be larger than the colder to be larger than the reference. In fact, we're going to take that this reference, we don't know what temperature is, right? So we just say, well, whatever it is, I just call the temperature of this thing here 1. And the units are Kelvin. We just call it 1 for now. Okay, so first let's look at the overall kind of energy balance of this. So what I meant by these two ways of going around, like directly here or this way around, are the same, is that if you look at all the energies, you're going to see that if you look at conservation of energy for each of these engines, well, we have that WA, this is what is the heat that goes from the hot minus the heat that goes into the cold. This one would be hot minus the heat that goes into the reference bath. And this one is the cold minus Q reference. Okay. Good. And now we say, well, all this heat, they must depend on some property of the temperature only, right? This was kind of the whole hypothesis. And then to test if this hypothesis is true or not, then we apply this to actual concrete physical systems, like an actual gas, or we have some model for how the particles move, etc. And then we can actually measure the energy that comes out and see if we can express it in terms of the temperature in this way. But the assumption for now is that it only depends on the temperature, right? Okay, so then we say, let's say that the heat is always some constant times some function of the temperature that we don't know. Okay? And one way of saying that this is our reference path is to just say, well, then this constant is, we're just going to call this constant the reference heat. So the heat that is deposited and coming from the reference path. Yeah. So we put here the QREF. QR. Okay. We could have chosen any other path to be the reference one, but we're going to choose this one because from the way we define here, we just say, well, this temperature, we'll just call it 1 degree. And now we say, well, this is a function of the temperature, but we've not defined what the temperature is yet, right? The temperature could be anything. And I'm just going to say this is what I'll call the temperature directly. Okay. So you can imagine this would be some T prime, and this new thing, this F of T prime is T, and I will just call this the temperature directly. Okay. Right, which we can do because we've not defined it yet. We just say, well, it's going to be it's going to be some function of the properties of the bath such that the heat depends linearly on this function. That's our definition. Okay, good. So now let's look at this work that's coming from engine C here. If we have this, then we have work C. Well, that's going to be Q hot minus Q reference. And that's what? That's just Q reference T hot minus 1. If we look at the machine B, that's this one here. We have again that W. No, sorry. Yes, B. That's right. It's Q cold minus Q reference. That's Q reference T cold minus 1. Okay. So now let's look at what's left in the in WA, and we can use this directly. We could also go do the same thing as here, but we can just do this directly. Well, then this is just Q hot minus, sorry. We could go either way, but let's say it's W3 minus, W hot minus, sorry, W of the machine C minus the work coming out of machine B. That's going to be QR T hot minus 1 minus TC plus 1. Right. QRef T hot minus T cold. So then what is the efficiency of machine A? That's WA divided by Q hot. Okay, so it's QR TH minus TC divided by QR TH. Yep. Let's just, oof, that's very large. Yeah. So we found the efficiency of this machine. Here, and it depends, like we saw before, it depends only on these two temperatures. And because we said before that the all reversible engines must have the same efficiency, then all reversible engines must have this thing. But we don't know what the temperature is yet. And to define the temperature, we can just think of any machine that is connected to this reference one. Okay, because here we said, well, this temperature is 1. So we can define the temperature of a hot bath in terms of just the efficiency of this thing. So let me give an example. To define what T hot is, we start with the efficiency of the machine C, for example. That's WC over QC. And this was what the QRef TH minus 1, because 1 was the temperature of the reference, 1 TH. So from this is equivalent to saying that you cut, and then you bring the T to the other side. T hot is going to be 1 over 1 minus tech. And this, you don't need to care that it's the efficiency of this particular machine C, as long as it's some reversible machine, you know that they're all the same. Yeah. You can do the same, exactly the same for T cold. So the conclusion is that we can define temperature by just having some model of reversible engines. How do you have a reversible engine? If you can run it one way or the other, and the work costs, like how much electricity they consume, for example, of running one way is the same as you get out running the other way, then you know it's reversible. If you know it's reversible, then you know it has optimal efficiency. Otherwise, you could build these perpetual motion engines. Okay. So now all you need is to have something that you call the reference, which, you know, it didn't need to be 1K. It can be something like, people who choose something like the boiling point of water, for example, at atmospheric pressure. 1K is like, 1 Kelvin is very, very, very low. You don't actually have access to this thing. So all you have access to is something like these two heat baths. But if you had it, then you could define the temperature of the hot one via just the efficiency of a machine, right? So you measure how much energy comes out, how much energy goes in, and from this you can define what the efficiency is. Okay? So conclusions, what we learned from here. Number 1 is, for all reversible heat engines, mu equals W over Q hot, which is always hot minus cold over hot, okay, which is smaller than 1. We can define the temperature of a bath by running this machine, right? From this unknown temperature to my reference temperature, right? So this was between hot and cold. We can define this as a temperature as being 1 minus mu. And a consequence of this is that you cannot extract energy from a single bath. Okay. Because look, if all you had was the same bath at the same temperature, up and below, right? Then the efficiency of the best possible machine is going to be mu equals, well, T minus T over T, which is 0. Yeah. So it does have this idea of passivity of like, if all I have is one bath, then I can't do anything from it. I always need to have 2 baths in order to extract some energy out. So what we do in statistical physics is to relate this temperature that is a very operational concept that just comes from what engines we can build to the microscopic properties of the system. Okay? So in the case of, we model the system as being an ideal gas. This means a gas where the particles are like little balls, like billiard balls that are shooting in different directions. And we make some assumptions about how they don't interact, etc. Then we have some model about how the pressure and volume and the average velocity of this particles relates to the temperature. Okay, but we will not look into this because that's the classical part. We want to look into the quantum thermal state. So our goal is to find a microscopic description, so a description of a density matrix for a system, which we can use to build, for example, this kind of heat engines and achieve this maximal efficiency. And then we'll know that we got the right state. Right? That's kind of the long way around that we did. Okay, we are reaching the end of the lecture, so maybe I will just say what the state is, and then I'll continue in the lecture that I'll upload today or tomorrow. Okay, so what is a quantum thermal bath? And like you saw in the tutorial, so say we have a system, let's call it A, with some Hamiltonian HA, and we want to have a state, so a density matrix that can only depend on this factor temperature of A, and of course it can depend on the Hamiltonian, but not more, right? That's the whole goal of the things we want to do. And it should satisfy the properties that if we have access to 2 baths, in state, this tau is against this density matrix, HA, TA, and you have a tau B of HB and TB, we should be able to build a heat engine, reversible, quantum heat engine with efficiency like we saw before. Let's say that the B is hotter than the A with this efficiency, right? So, and it should not depend, for example, on the form of the Hamiltonian. This is like our ideal heat bath. And again, so if we have only one, it should not, this should be 0 in particular, and it should have these other properties like this typical typicality. Yeah? And like we saw before, so it should have this typicality and passivity, meaning that if you have just one heat bath, you can't extract anything from it. So what I'll do next is to prove that this state, if you have, if you define it like this, E minus KB, this is a constant H, A, divided by Z, where Z is the trace of that. So all we want at the end is to have a normalized density matrix. So we just need to have trace 1. So we just divide it by the trace. That we have something like this. This actually need like a thermal state. So this is kind of our microscopic description of a system, which should have all these properties. Okay, so this is what we'll do next time. I will take this state, show some of these properties. We will not prove them, but I'll just kind of give you arguments why this should be the case, and this will be proven in the next semester course. But then the thing we'll do is to try to build this heat engine. And it could be that these heat engines, we said nothing about their designs, right? They could be anything, like a computer can be a very complex system. But it will turn out that these heat engines can be made very, very, very simply. So only made of a few qubits. By few, I mean less than 5 qubits. Yeah. So we'll see how we build these quantum heat engines, and then finally we'll apply it to the Erasure protocol. Okay. So we are going to finish here, and I'll upload the next lecture soon. Thanks.